Good afternoon. My name is Hyun Jung from Korea University, Seoul, Korea. So first of all, many thanks to committee member and my friend Dr. Young-jin Jo for inviting me in this symposium. So in this talk, I want to briefly summarize some recent research work in our group related to the film coating processes, film coating and drying processes, focusing on the particle motion, particle dynamics in the particle suspension systems. So before starting my main talk, I want to introduce my research background. I'm worrying that my research topic is maybe somewhat different from the topic of this conference. So as a rheologist, my research field include fluid dynamics and stability in rheological processes, including polymer processing and the coating processes and microfluidic systems. So we usually combine shear extensional rheological properties of complex fluids, so particle suspension, and then experimental observation of flow behavior in rheological processes, and theoretical simulation and modeling for nonlinear stability or sensitivity dynamics in microfluidic systems. I also interested in many kinds of film processing. The first case is film casting and the film blowing process. Second speaker introduced the film blowing process. We have a very small scale film blowing extruder, as shown here. So to produce the extruded polymeric film. So we mainly investigate flow instability occurring in these processes. For example, I'm sorry. So could you click the right, upper right here? Oh no. 요 가운데 거랑 여기. You can see some periodic oscillation of state variable in the film casting process, and also please click the next figure. One more next to the helical motion in film blowing processes, and also second is UV curing process and thermal curing or dual curing processes to produce highly cross-linked organic film. So mostly representative process is automotive clear coat layer. So we try to establish relationship between the chemorheology of organic coating, the real-time cross-linking behavior or curing behavior during the curing process, and physical properties of finally cured films and so on. And third part is liquid film coating for making particulate suspension film onto the moving substrate. So this is the main process of this talk. The film coating is a replacement of gas at moving substrate surface by the coating liquid. So as shown in this simplified coating line, for example, slag coating, the coating liquid fed from the feed will be distributed and metered inside the coater, and then deposited on the moving web, and then dried and cured in the next step, final step, to make particulate suspension, particulate coating films. So in many cases, particulate suspension or slurries are used to make many functional films like platform net displays, lithium-ion secondary battery, fuel cell, and so on. So similar slide here. So representative coating applications using slurry particulate suspensions, lithium-ion secondary battery, or polymer exchange membrane, fuel cell, and water electrolyzers, and so on. So these particulate coating films usually produced using the slot coating processes, as I mentioned before here, including the sequential coating operation and drying operation. There are many key issues in slot coating processes using particulate suspensions. So we try to understand these topics in each case, so including the suspension rheology and internal slot die design and external slot die design for the uniform coating operation, and the fundamental physics for particle motion in coating flow and particle distribution along the film height in a wet film during the drying. So in this talk, I will explain some results on the particle motion in coating flow and particle distribution during the drying in two cases. So here is one question. When using particulate suspension or slurries in the continuous coating line, as shown here, if we feed particulate suspensions, well-distributed mixture of coating liquid to the coating line, can you always produce coating layer with the very uniformly distributed particles as a final product? But in many cases, answer will be no. In the coating flow regime, so particles can show non-uniform distribution due to the external force like gravity or sedimentation, and inhomogeneous shear flow, Poisson flow, and finally inertia even at the homogeneous linear shear flow, Couette flow. Also in the drying step, we usually observe non-uniform particle distribution along the film height during the drying. So we try to numerically understand the particle dynamics in the various coating flow field and the drying processes. So first part is particle motion in suspension coating flows. So this study was originally motivated by the slot coating processes as shown here. So in general, particulate suspensions are applied to make functional film, such as electrode, lithium-ion secondary battery electrode, or the fuel cell electrode, and so on. So coating liquid, in this coating slot die geometry, the coating liquid will experience the pressure-driven flow, Poisson flow here, and then coating liquid will experience combined drag-driven flow and the pressure-driven flow in the very narrow coating gap region here. So particle distribution will be changed due to the shear-induced migration in the inhomogeneous shear flow. Also, if we consider polydispersed particulate suspensions, we can see some segregation behavior between the large particle and the small particles. So to numerically solve some particle motion in flow field, so we applied continuum-based diffusion flux model. This is some phenomenological model developed by the Professor Phillips, and then mesoscale particle-based lattice-Boltzmann method. So more detailed descriptive method will be explained in this. So the first, we confirmed that our 1D and 2D continuum-based model and the lattice-Boltzmann method well predicted experimentally observed particle concentration distribution reported by the real group in the Poisson flow. These are our result. Let me briefly explain some result on the migration and the segregation behavior in bidispersed spherical particle suspensions. Both are left figure, left movie. Let's see the left movie. Yeah. So you can see some monodispersed particle and the bidispersed particles are moving within the slit channel under the pressure-driven flow field, as shown here. In that case, monodispersed particle, two cases, will migrate toward the mid-plane due to the shear-induced migration. So particle will move from the wall to the center, so from the high shear rate regime to the low shear rate regime, as shown here. In the bidispersed case, finally, we can see some segregation behavior between the large particle and the small particle. So due to the different shear-induced diffusivity. So large particle first move toward the mid-plane, and the small particle will be depleted from the mid-plane, moving toward the wall, as shown here. Clear segregation behavior. Also, we found this segregation behavior using modified continuum-based model, diffusion flux model. So good agreement between the transient response of segregation behavior from the LBM and the diffusion flux model. We also obtained result segregation behavior of bidispersed suspensions in the wall-bounded linear shear flow field. In that case, particle-based Reynolds number is very important. 0.1 is a magic number. So Morris group explained it if the particle-based Reynolds number is larger than 0.1, particles will experience wall. So moving toward the wall due to the lift force. So 0.1, please remember that. So let's see the movie two cases, two different Reynolds number cases. In the first case, small particle Reynolds number is less than 0.1. So small particle will be uniformly distributed. And large particle will experience lift force and moving toward the mid-plane here. Whereas in the second case, both Reynolds number are larger than 0.1. So small particle show the parabolic concentration distribution. In that case, large particle move toward the wall, not mid-plane, due to the concentration gradient of small particle, due to the diffusion polarity effect. So we have further extended to non-spherical particle system and various flow field, because many coating applications consider many kinds of particles covering the non-Brownian case and Brownian case here. Also, these particles will experience very complicated flow field, like a shear dominant flow, extensional dominant flow, and mixed flow, and so on. So up to now, we only focus on the motion of rigid colloidal rod particles and their orientation ordering depending on the flow field. So we successfully designed rigid rod, colloidal rod, as a non-overlapping chain of spheres, as shown here. So in that case, we first check the basic feature of rigid rod in the two cases. The non-Brownian rod in the simple shear flow at high particle number regime will show Jeffrey orbit like that is a very classical movement of rigid rod in the simple shear flow. So exactly correct. Good agreement. And in the second case, Brownian rod at the particle number 0 in quest liquid cases, we compared mean square displacement of single rod of position at the position and the orientation data, as shown here, giving the good agreement between the LBM simulation and the slender body theory model. That is a classic model for the Brownian rod in the quest liquid here. Also, we found that the good agreement between the translational and the rotational diffusivity from the two methods. After checking the single rod dynamics, we extended to the semi-dilute or dilute suspension system to investigate flow-induced orientational ordering of colloidal rod in various flow field. Let's take a look at the movie showing the transient movement of colloidal semi-dilute to dilute colloidal rod in the various flow field as shown here, in wet flow, quasi-flow, shear flows, and extensional flow, and the mixed flow cases. So based on this result, we can estimate orientational order of colloidal rod following the flow field in each cases. So depending on the Packer number, rotational Packer number. Rotational Packer number is the ratio between the strain rate magnitude and rotational diffusibility. So fortunately, we found that we obtained one sigmoidal curve for orientational order parameter along the Packer number. So we found that the orientational order parameter is increasing with rotational Packer number regardless of flow field, single master curve, not except a high Packer number regime. Also, this simulation supported experimental bifringence data reported by another group. So this is recent ongoing work. In the 2019, this group reported that colloidal rod will show very interesting side-to-side swinging motion near the confined wall, near the wall. So we try to demonstrate this behavior using the lattice-Boltzmann theory. So using this colloidal rod, we tested the motion of colloidal rod within the very narrow confined channel wall. You can see some move colloidal rod, but different color. All blue colored particles are moving near the wall, and the blue-like colloidal rod are moving the mid-plane region. So let me focus on the all blue color moving near the wall, as shown here. Okay. So we found that the colloidal rod are periodically swinging near the wall. If the particle is initially somewhat tilted up and down near the wall, as shown here. And also, we increased particle concentration to the semi-dilute regime, as shown here. So you can see some worm-like particles are moving the very confined channel region, as shown here. So we increase the particle concentration. So you can see some two different colloidal rod, all blue colored, moving toward the wall, and blue colloidal rod are moving near the middle region. So we compared the transient position and orientation of colloidal rod around the center and the wall. So as the concentration increase, so number of colloidal rod is increasing near the wall, as shown here. However, the number of rod in the middle plane keeps constant without concentration, regardless of concentration. Also, considering the orientational rod, colloidal rod moving toward the wall are randomly distributed, and colloidal rod moving the mid-plane show the very highly aligned, as shown here. You can see some the orientational changes between the two colloidal rod. So second part is a drying, vertical drying of colloidal suspension wet film. So in this case, we only consider simplified vertical drying, one-dimensional vertical drying, not neglecting the edge side. So there are two drying stages. So first is a wet stage. Air-liquid interface is linearly moving down, as shown here. And the second is a moist stage. So just evaporation through the capillary pore without change of any structure. So we'll only consider wet stage to check the particle dynamics during the drying. So most important parameter for drying process is a Packer number. Packer number is the ratio between the evaporation rate, evaporation speed, and the diffusibility. So in the low Packer number, slow evaporation, particles will be uniformly distributed along the height during the drying. And high Packer number, the fast evaporation induces inhomogeneous particle layer along the film height, showing the very highly densely packed layer at the interface top. So in general, there are three regions in the drying film at the intermediate to high Packer number regime. So at the top, so packed region and the diffusion region in the intermediate region, and bulk or dispersion region at the bottom. So we try to numerically understand that this drying picture by changing the Packer number, slow evaporation, fast evaporation for the monodisperse and bidisperse suspension cases. The first case is film drying for monodisperse suspension films. So we conducted lattice-Boltzmann method simulation by changing the Packer number for neutrally buoyant particles dispersed in a Newtonian liquid. So you can see some transient movement of particles during the drying at different Packer number. So frame time was slightly adjusted so that the interface were in the same position. That is very slow drying cases. In the low Packer number, you can see some particles are uniformly distributed along the film height during the drying, whereas at the intermediate or high Packer number regime, the fast evaporation induced that highly densely packed layer at the top, showing the inhomogeneous particle distribution. Also, we developed some continuum-based drying model for interpret that behavior. So well-known drying model is Laus-Zimmermann model. So we modified this model by changing the diffusibility, collective diffusibility term with the two parameters. So giving the good agreement between the LBM simulation and modified model for predicting the transient the drying dynamics under the different concentration and the Packer numbers. The second is particle drying of bidisperse, large particle and small particle, bidisperse colloidal suspension wet film. I think most important issue in this case is stratification by particles by their sizes, depending on the Packer number, particle size ratio, and the volume fractions. So in general, slow evaporation induced large on top, large particle positioned on the top, large on top, auto stratification. So high evaporation made the small on top structure. So we call the inverted stratification. So we try to compare this stratification by changing the Packer number. So there are many experimental observations and simulations data to explain the stratification here. Also, one comment here, the theoretical model have been developed and suggested in many cases as shown here. But this model emphasized that explicit solvent effect, so-called hydrodynamic interaction between the particles and solvents should be considered to predict stratification. So we try to compare. So I'm sorry. Yeah. So I'll finish as soon as possible. So we try to compare the two simulation results, the implicit solvent method, Langevin dynamics, and the explicit solvent method, hydrodynamic, lattice-Boltzmann method with hydrodynamic interaction. So we try to discern the effect of hydrodynamic interaction on the stratification. Let's take a look at the movie. So when the Packer number increasing, LD, implicit solvent method show the change of stratification from the large on top, small on top, and mixed case. Whereas LB case show the change of stratification from the large on top, just mixed case, suppressing the small on top cases. So we especially measured mean height of large particles and the small particles at the underwet stage, the final stage. And using this data, we constructed this degree of stratification along the Packer number. So in that case, implicit solvent method without hydrodynamic interaction showed large on top, small on top mixed case with increased Packer number, and LD with hydrodynamic interaction case showed the large on top, just mixed case, suppressing the small on top stratification due to the hydrodynamic interaction between the large particle solvent and the particles. So I will conclude my talk by just introducing the ongoing work. Particle migration, the slot coating bead flow, actual flow, using the continuum-based diffusion flux model as shown here. And we are now considering the gravitational instability during drying. So we found that some evaporation-induced Rayleigh Taylor instability when after the sudden stop during the drying, as shown here. And also, we further increase size ratio to clearly show the stratification of the bidispersed drying films. And final is drying of granular droplet particles. So we can see some small on top, large on top of sphere drying cases. So thank you very much for your attention.
Any question from the floor? Yes.
Thank you for your nice presentation.
Thank you very much.
I have a
Oh, yeah.
It's my understanding you presented simulation results
Yeah, you're right.
and then tested the real
It's-
the coating test. EPS, what
Okay.
kind of nanoparticles
Yeah.
you used?
Yeah.
And
So,
the last one, one
yeah.
more.
Oh, yeah, yeah.
The last one is, can you give us some recommendation to apply this coating method
Yeah.
in food packaging applications?
Food packaging.
Yeah.
Oh, yeah. Two questions are very difficult. So actually, I could not conduct experiments because I'm focusing on the processing or dynamics, fluid dynamics, not the final property. So it is very difficult to observe the real-time particle behavior
Okay.
during the
Just
flow.
recommend
Yeah,
some-
and then so I would like to compare the experimental data in the next time. If you, so we tried to find the literature, so we could not actually conduct the experiment. And the second case, I'm not sure. So I have no idea about the packaging film, but if we apply the particles as a additive or something like that, so I can, this result can help to control the particle distribution. I'm not sure, discussion in making the packing film.
when
Packaging
you do
film.
the particles, what do
Yeah.
you usually say?
So in my case, that is nanoparticle. So some micron, micro size scale. So I only consider, yeah.
So yes, a generally question.
Yeah.
So when you see this kind of the work, the computational work,
Computational work, yeah.
this work is computational work.
Yeah.
But I'm not an expert in
Mm.
dynamic, fluid dynamics and also computational
Mm.
simulation.
Mm.
Because many of times I just thinking, how do we correlate
Mm.
this type of computational work to real industrial works?
Ah.
Like you said, this
Yeah.
this study just gives some result and estimate
Yeah.
how the coding process
Yeah,
will
right.
go.
Yeah, very important question. So actually, in the today topic is somewhat academical, not industrial application. But I applied computational to the coating processes to optimally design the slot die and the operating condition. So in that case, I try to compare industrial experimental data and our simulation data in that cases.
Our research team is also working on the lithium-ion battery, so
Oh,
this is very interesting.
Oh, yes.
So, but for fabrication of the cathode, we prepare the active materials and the CNT, and sometimes including the binders. That is more complex systems.
Yeah.
So how can we apply your ideas of that? I mean, if we want to change some solvent, can you calculate that?
So I think my particle dynamic system is a very simple cases, just mixture of hard sphere and the solvent. So I think the many slurries include so small particle and polymer and irregular particles and so on. So I think I can give some fundamental physics about the very simplified particle dynamics, and then we try to correlate that result to very complicated slurry systems in the next step. Very difficult case.
Thank you, Professor Jung.
Thank you.